Hello, and welcome back. Today I will be going over the code for GJK. I will be following roughly the same outline as in the theory video, going over the skeleton of GJK, filling out the functions, and then stepping into the barycentric calculations. So with that being said, let's begin. So starting off here, we're going to begin by defining an iteration limit, and this will just simply be to make sure that we don't loop for infinity. Then we go ahead and set the distance equal to infinity. I would like to mention a lot of this code has actually changed since the recording of this video, but the underlying principles are the same. So we're going to loop for each iteration, and first we're going to find a support point using the geometry, the hull, and the current search direction. After this, we'll want to check if the point is a duplicate, and we'll make sure that it's not by checking if the current simplex already contains that support point. If it does, we return true for no collision. After we've ensured that the support point is new, we also want to make sure that it is always in the front. So we will use the push front function for the simplex, add the support, and then we want to attempt to remove any non-contributing vertices. This is actually one of the changes, by the way. That function no longer takes in the closest point, but rather returns it. Next, we'll want to check if that closest point is contained inside the origin. Oh, I'm sorry, actually, we just check if the simplex contains the origin. We don't use the closest point yet. If it does contain the origin, we return false, indicating that there is a collision. After this, we'll want to calculate the distance to make sure that we're making progress towards the origin. And then we just do a simple check to make sure that we're not either further or equal to the previous distance. And then finally, if all that is fine, we update the search direction and the distance for the next iteration. And the search direction will be computed based on the simplex size. All of this can really be found in the theory video. This is the supplemental code. However, at the end of this, we will go ahead and return false, just in case we missed an exit condition or something. Sorry, return true to report no collision. So we will start now with the functions, beginning with contain support. This is going to be a lambda function which returns true or false, and it's going to be checking if there is a duplicate. And it does this by checking if the current simplex point and the new simplex point share the same A and B vertex indices. If we find a point in the range, we go ahead and return true, meaning that this is a pre-existing support point and we have begun to cycle, so we need to end. Now we'll take a look at the call simplex function. This has changed quite a bit, so please look at the Git, but the idea still remains the same. First, we are going to find the closest point using the find closest point on simplex function. Then we are going to capture the weights calculated from the barycentric functions that we will get onto later. After we have the weights, we're going to go ahead and switch on the simplex size, and we are going to attempt to call any of the simplex vertices whose corresponding weight is less than or equal to 0. If we detect that the weight is less than or equal to 0, we create a new simplex with the remaining points, though those weights themselves may be negative. And then we return the call simplex vertices again, basically iteratively or recursively stepping through this function, taking off 1 degree at a time. There probably is a way to do this in one shot, however, I could not get the simulation to remain stable without using the recursive approach. So if you figure it out, please let me know. But nonetheless, we're going to go ahead and fill out the remaining case 3 and 4, simply following that rule. We also need to make sure that we add a check here at the beginning to account for if the origin is contained. The weights will not be set. So moving on now to actually checking if the origin is contained, we'll go ahead and set some tolerance limit, which essentially creates an artificial radius that we'll be checking against. Once more, we're going to switch on the simplex size, and in case 1, we want to check if the origin is close enough to the simplex. So we simply check if the magnitude squared of the current simplex point is within the tolerance. Next, we'll essentially create a capsule with the line segment that is the current simplex, using that tolerance as a radius to inflate around that line segment. And then here we're going to just do that tolerance check with the closest point on the line segment returned from the origin and the 2 simplex points. In case number 3, we are going to use the surface plane and create essentially what's called a fat plane and give it some thickness, the size of the tolerance, and likewise we're going to do our check again. However, in this case we only need to check the W component, and you can check out that formula up there as to why that works. And then finally, if we get to case 4, we were unable to call the simplex before, so we contain the origin, and we just simply go ahead and return true here. And this will cause us to exit the whole GJK iteration. And finally, finishing with search direction, once more we'll switch on the size, and depending on the case, we're always going to attempt to return a direction that points towards the origin. So in case 1, it's simply just negating the first point. In case 2, we're going to want to use that cross product trick to give us a vector, or I guess a bivector, that points towards the origin and is oriented with AB and AO. And then in case 3, we'll just use the surface normal of the plane. However, we need to check if the origin is above or below the plane, and if so, we return the appropriate surface direction. And once more, we use the fact that we can just check the W component of the plane. And there will be no case 4 because we should never get to this point if we determine that we have a simplex of size 4. And one last function, forgot about this one. This will be actually finding the closest point on the simplex. This is just, again, another switch, and it will call the appropriate barycentric function with the origin as the query point, and then the simplex points and weights for the vertices and corresponding weights. Just remember that simplex point 0 is always point A, simplex point 1 is always B, and so on and so forth. Alright, so now we can start looking at the barycentric functions. The first one is super simple. We just simply return the point and set the weight to 1. It's going to be easier than that. For barycentric 2, we want to compute the fractional lengths of the subsegments AQ and BQ. These fractional lengths will be corresponding to the weights themselves. And then we assert that U and V are basically 1, and if they are, we go ahead and check the Voronoi regions. And if both the Voronoi region checks pass, we just simply return the combined point from the two weights. So now we'll begin Barycentric 3, and this is where things start to get a little more involved. We're first going to start by creating a lambda function to calculate the signed triangle area. This function will take in a query point P, two vertices V0 and V1, as well as the triangle normal ABC. The whole purpose of this function is to calculate the signed triangle area of the subtriangle provided by P V0 V1. The way this works is we compute this the area with the cross product, and then dotting it with the normal of the base triangle gives us the signed area. After we have this function, we'll go ahead and create some helper variables, and these will be tracking the UVs of the edges of the triangle. We'll go ahead and call the barycentric 2 function, and this will set the weights of the corresponding edges. Once we have these weights, we'll go ahead and set the primary weights of U, V, and W to 0, and we'll begin doing our testing. The first thing we want to do is test the vertex regions, and we'll be following the tests as described in the theory video. So if you want the specifics for what vertices or edges are being tested against what, I will have that linked below. But if we detect that we are in a vertex region, we go ahead and return the closest point as being simply that vertex, and then that will internally set the vertex's weight to be 1. Subsequently, it'll leave the other two weights as 0, and they will be culled. Now, after we've checked the vertex edges, we're going to, or the simplex vertices, we're going to check the simplex edges. So now we're going to use our signed area calculations. The first thing we're going to do is just get the overall area of the main triangle, and then we're going to invert that magnitude. Then we're going to calculate the three areas of the subtriangles, QBC, QCA, and QAB. Once we have those, we will compute the weights U, V, and W of the main triangle by multiplying the fractional area with the overall area of the primary triangle. Next, we'll want to test the edge regions. And to do this, we want to make sure that the query point projects inside the edge and is outside the triangle from the complementary vertex. If we detect this condition, we go ahead and set the primary weights equal to the corresponding edge weights, and we set the complementary weight to 0. And then we return the closest point as being a combination. There's no need to call Barycentric 2 again to return here, as we already have those values stored. Now finally, if all of those edge regions pass, we just do some assertions to make sure that we are in fact inside the triangle region, and we will compute with weights and then return the closest point as being the combination thereof. Now we can begin the actual barycentric 3. I just now realized I've been calling them the wrong names. The barycentric name corresponds to the simplex weight, which is 1 minus the total number of points. So the actual simplex 3 begins by setting all the vertex weights, or all the simplex weights, to 0, and then doing a degenerate check to see if the tetrahedron, all the points are coplanar. We do this by calculating the parallel pipe head of the input points, testing against some tolerance, and if that test goes ahead and succeeds, we determine that the tetrahedron is degenerate, remove the oldest point D, and return the barycentric 2 calculations with A, B, and C. After that, we'll go ahead and test the vertex regions. We start with vertex A, and we will create some vectors that point from vertex A towards the query point and the remaining simplex points. And I'll again link the theory video below, but if you remember from the theory video, the point of the vertex tests is to determine that the vector from the vertex point in question towards the query point is in the opposite direction than that of the vertex point towards the remaining simplex points. We go ahead and compute our dot products and then create our Boolean values just to make it a little cleaner. We'll go ahead and do our projection tests, and if we determine that the projection is outside the simplex with respect to the vertex, we reduce the simplex down to that vertex point and return the barycentric 0 calculation. Next, we will move on to testing the edge regions. We begin by computing the surface normals of the two triangles created by the, or joined by the edge in question. And after that, we will create the edge normals. And we do this by crossing the edge with the corresponding face. What this does is it returns us back a vector that points towards the edge in question. Once we have our edge normals, we go ahead and check our projections with the query point. The first two checks are to make sure that Q projects inside of AB. We want to make sure that the point is inside the line, but we also want to make sure that the point is along the line. So we make sure that Q also projects towards the normal of the edge itself. So we want to check the dot product of AQ and NAB in this case, and AQ and NBA when checking edge AB. And then subsequently, we just supply the appropriate edge combination and reciprocal for each pair. We finish with our evaluation, and if our evaluation turns true, we return the Barycentric 1 calculation with the edge, the vertices of the edge and their weights. Next, we will be testing the face regions, and for this, we simply want to check if the face created by the points which exclude that which is in question is basically a separating plane between the query point and the complementary point. So for example, when testing face ABC, we are checking if triangle ABC separates Q and D. We go ahead and compute the parallel pipe head and get the signed volume, and then the multiplication of those two should be negative if they are in fact separated by the plane. If the point is separated from Q, we return the barycentric 2 calculation of the appropriate, or we return the barycentric 2 calculation using the vertices which create the face that separates the point and the complementary vertex. So that is all for today. Thank you for your time. I will be linking the GitHub below to the most up-to-date code for the algorithm. I will see you in the next one with the SAT algorithm. Thank you very much.